we saw in the earlier lecture that the origin of the electric and magnetic fields is a charge. The effect of a charge is felt by a quantity what is called the electric field. However, when the same charge is kept in motion, it constitutes a current, and then the presence of current is felt by a quantity what is called the magnetic field. So, we can take current as the origin of the magnetic field, and today we try to establish the relationship between the current and the magnetic field, and then we also define the parameter what is called the magnetic flux density and its relation to the magnetic field, and then we will go to some other laws like Ohm's law and other laws of electromagnetics and formulate these laws in the mathematical form, what are called the Maxwells equations. So, if I have a current element which is a small piece of, let us say, a wire which is carrying some current I, the length of this current element is, let us say, given by dl, then at some point in the space which is at a distance r from this current element, and let us say this is denoted by vector r, the magnetic field due to this small element, let us denote it by dh, where d gives you the incremental value of the magnetic field. So, dh gives me the magnetic field due to the small current element, that is equal to I dl cross r unit vector in this direction divided by 4 pi into r square. So, the magnetic field at this location point P, let us say, is given by this expression. So, the magnetic field is proportional to the current, it is also proportional to the length of the wire over which the current flows, and it is inversely proportional to the square of the distance from the element. dl cross r unit vector, that is the cross product of dl and the unit vector in this direction, r direction. So, if I apply the right hand rule, the dl cross r gives me a direction which goes inwards the paper. So, at this location the magnetic field will be going inside the paper, so which we denote by the cross. So, the direction of the magnetic field is inside the paper at this location, and the magnitude is given by the magnitude of this expression. Since the dimension of dl is length and you are having a length square in the denominator, the unit of the magnetic field is the current per unit length. So, that is amperes per meter. This is the magnetic field strength at this location P due to this current element. Many times the magnetic field strength is simply called magnetic field, and what we find is that this quantity is not related on any of the medium parameters. As long as this current is I, the length is dl, no matter what medium is surrounding this current element, the magnetic field produced at this point will be this. The quantity then which relates to the medium parameter is the magnetic flux density. So, the quantity which we define now, what is called the magnetic flux density, and that is denoted by B, that is equal to a medium parameter what is called the permeability of the medium times the magnetic field strength. So, that is H. So, this quantity mu is called permeability of the medium. Depending upon the magnetic properties of the material, the value of the permeability changes. So, for free space, the value of permeability is denoted by free space. The permeability mu is denoted by mu 0 and its value is 4 pi into 10 to the power minus 7 Henries per meter. Then as we defined in the case of the electric field or the media for the electrostatics, if I have a material whose permeability is mu, the ratio of mu and mu naught, that is the ratio of the permeability of that medium to the permeability of the free space, is called the relative permeability of the medium. So, we have a parameter relative permeability of a medium, which is the medium parameter, that is mu r is equal to mu divided by mu 0. If you take magnetic material, typical value of mu may range of 10 or even sometimes 100. So, the magnetic flux density at any location B is related to the permeability of the medium and the magnetic field strength, which is related to the current which is producing that. Unit for B is Tesla, or more commonly used is Weber per meter square. So, essentially this quantity B tells you the density of the magnetic lines of forces at a particular location. So, this quantity essentially is telling you some kind of vectors which are oriented, and that is the reason this quantity is a vector quantity. Same is true for the magnetic field, that we are finding the effect of this current at this location. So, we can define the magnetic field even alternatively, as we define in terms of the electric field, that is the force experienced by per unit charge due to the presence of a charge. Same thing we can define for the magnetic field also, that is the force which will be experienced by a unit magnetic pole if it is placed in the vicinity of a current. So, essentially the magnetic field or magnetic field strength and the magnetic flux density are the vector quantities. The next thing which we have in our discussion is what is called the Ohm's law, and that is the relation between, as we commonly know, between the voltage and current flowing in a medium or in a circuit. However, in the general form of Ohm's law is the relationship between a quantity what is called the conduction current density and the electric field. So, if I take a very general medium where the conductivity of the medium is not constant, then it is not very meaningful to define the total current for that medium. So, normally what we do, we define a quantity what is called the conduction current density. So, if I have, let us say, some conductor like that, and let us say the medium property which is the conductivity of the medium vary inside this, then I can define the quantity what is called conduction current density. So, it is the current flowing per unit area of this conductor. So, again, since it is having a direction in which the current is flowing, this is the vector quantity. So, it is the amperes per meter square, that is the unit of this. So, amperes per meter square, and this current is now flowing because you are having some electric field which is related to the potential. So, we have seen the electric field is related to the potential gradient of potential, the potential difference. So, if you go from the circuit Ohm's law, we have a relation between the voltage and current, which is a proportionality relationship, and we have a parameter proportionality constant which is what is called the resistance. Here we have a parameter which is the conductivity of the medium, which is inverse of the resistivity of the medium. So, essentially we have a relationship between the electric field which is driving this current and the conduction current density. So, the Ohm's law in in general form is the conduction current density J, that is equal to the conductivity of the medium times the electric field. Again, in both the cases, as we saw in the previous case, the relative permeability of the medium mu or mu r and the conductivity of the medium sigma in general could be 3/3 matrices. So, if you take a medium which is isotropic medium, then the quantity mu r and sigma are the scalar quantities, whereas if the media are an isotropic medium, that means if the properties of the medium depend on the direction, then in general mu r will be a 3/3 matrix, the conductivity sigma will be a 3/3 matrix. So, this quantity conductivity in general could be a 3/3 matrix for an isotropic medium. And meaning of this is exactly same as we saw in the case of electric field, that there if the medium is isotropic, then the direction of the displacement vector and the electric field are same. Same thing will happen in the case of the magnetic field also. So, if the medium is isotropic, then the direction of the magnetic field and the magnetic flux density, that will be same, but if the medium is anisotropic, then these two directions will not be same. Same is true for the conduction current density and the electric field, that if the medium is anisotropic, then the direction of the electric field is not same as the direction of the conduction current density. So, in general, if I have an anisotropic medium, then the direction of the electric field and the conduction current density will be different. With this basic introduction of the parameters, now we can go to the physical laws which give you finally the Maxwell's equations. Now, there are two ways to look at Maxwell's equations. One is that you treat Maxwell's equations are mathematical postulates and the physical laws are the experimental verification of those postulates. Other way of looking at it is we have physical laws and then try to represent these physical laws in appropriate mathematical form that gives you the Maxwell's equations. Both have its merits. That is, if I say that the Maxwell's equations are the mathematical postulates, then they are very exact. So, what we say is, if we take this as the postulate, then all the experimental errors and all that do not come into picture. So, these are very exact form of these equations, and then these are simply validated or verified by the experimental laws. However, one can ask a question, how do you reach to these postulates? One cannot simply come up with these mathematical forms without having a background. So, certainly the background was in the physical laws. So, first the physical laws came, just the curiosity of the relationship between the magnetic and electric fields led to these physical laws, and then the mathematical formulation guided us to get this mathematical form, what is called Maxwell's equations. So, if I go by this picture that the Maxwell's equations were guided by the experimental laws, then the advantage is that we will always try to see the phenomena in physical terms. So, if we have any electromagnetic phenomena and if we say that the origin of this lies in the physical laws, it will be always useful to look at every phenomena of electromagnetic physically. However, if you treat these equations more like mathematical postulates, then one may get lost into the mathematical manipulations of these equations. So, from the exactness point of view, the mathematical postulate is, it has merit, but seeing what physically is happening first understanding the physical laws and then getting the Maxwell's equations has a merit. What we will however do here, we will state first the physical laws and then using the vector identities and the theorems which you have mentioned earlier, the divergence and Stokes theorem, we will try to get the mathematical form and then we will get finally the Maxwell's equations. So, the very first law which governs the relationship between the displacement vector or the electric field and the charge distribution is what is called the Gauss law. The Gauss law states that the total displacement coming out of a closed surface is equal to the net charge enclosed by that closed surface. So, what that means is, if I have a closed surface like that, and let us say we have the charges distributed inside this closed surface, I find out the net displacement which is coming out of this surface, and that net displacement will be equal to the total charge or the net charge enclosed by this surface. That is the Gauss law. In general, the displacement vector will be varying as a function of location on the surface. Also, it will be oriented in different directions, but the net displacement vector which is coming out of the surface will be the component of this normal to the surface at that location. So, if I consider, let us say, a small incremental area on this surface, let us say it is given by dA. So, dA has, as we saw, the area has a direction which is given by its normal. So, this is the normal to the surface which is outward normal, and that any location here, let us say this is the direction of the displacement vector. So, the outward displacement which will be coming from this small area will be the dot product of these two. So, it is d dot dA, that is the component of the displacement vector in the normal direction. Once I get that, I can add all those contributions from all the areas on the surface, and I will get the total displacement coming from this closed surface. Then let us say in general we are having charges which are distributed inside this surface, and that can be characterized by the charge density inside this surface. So, let us say I have the charges which are distributed in this closed surface, which are denoted by the volume charge density denoted by rho. So, this is representing the density of the charges inside this volume. So, its units will be coulomb per meter cube. So, if I add up all the charges inside this volume, I get the total charge enclosed by this surface. So, integrating the displacement vector over the surface, I get the total outward displacement from this closed surface. If I add up all the charges which are lying inside this volume, I get the total charge enclosed by this surface. Then from the statement of the Gauss law, these two are equal. So, if I write down mathematically, this Gauss law can be written as follows: integration of the displacement vector over the total surface will be d dot dA integrated over the entire surface, closed surface. So, which I can write as a closed surface d dot dA where this surface is denoted by S and this volume is denoted by, let us say, V. So, this quantity represents now the total outward displacement from this closed surface. From the Gauss law, this is equal to the total charge enclosed by the surface. So, if I find out the total charge in this volume, rho into dV over this volume V, that gives me the total charge enclosed by the surface. So, mathematically the Gauss law can be written as simply as finding out the total displacement integrated over the surface and the total charge integrated over the volume. Once I get that, then I can apply divergence theorem to this Gauss law statement and I can convert this surface integral to the volume integral. So, as you have seen from the divergence theorem that this thing can also be written as the triple integral over the volume del dot d integrated over the volume. So, that is equal to the volume integral rho into dV. So, this is from the divergence theorem. So, if I apply divergence theorem to this integral now is converted from the surface integral to the volume integral. I can bring this term on this side and I can write this is over this volume V del dot D minus rho dV, that is equal to 0. Now, this relationship or this integral must be true for any arbitrary volume. That can happen provided the integrand is identically 0. So, this essentially gives you del dot D is equal to rho. So, the Gauss law, if I write in the integral form, it is this, but the same Gauss law can be written in a differential form, which is this. So, if I take divergence of the displacement vector at any location, then this is related to the volume charge density at that point. This relation is a point relation. That means we can apply, go to any point, find out what is the volume charge density at that location. If I know the displacement vector at that location, then find the divergence of the displacement vector at that location, I can get the volume charge density. So, the Gauss law can be applied depending upon the situation in the integral form and it can be applied in the differential form. Later on we will see that differential form has limitations, because differential form assumes that we have continuous media. So, the properties of the medium do not suddenly change, there is no discontinuity in the medium properties. So, whenever we are having boundaries where the properties of the media suddenly change, that time the differential form is not applicable because the derivatives do not exist. And that situation we go back to the original form of this law, which is the integral form of the law, and that will be true in other laws also, which we will discuss in the following. So, in all situations the integral form of the law is applicable. However, if the medium is smooth continuous, then you can apply the differential form of the law also. Now, this law in general is true. So, the divergence of the displacement vector is the volume charge density. However, we have seen the displacement vector is related to the electric field. So, we have the relationship D is equal to epsilon into the electric field. if we assume that the medium is homogeneous, that means epsilon is not a function of space, then I can substitute for d into this, and epsilon is not a function of space, epsilon can be taken out from here. So, the Gauss law can be written as del dot of epsilon into E, that is equal to rho for homogeneous medium epsilon is not a function of space. So, the epsilon can be taken out. So, I get del dot E, that is equal to rho upon epsilon. So, we can apply this Gauss law for a homogeneous medium for the electric field directly instead of going to a displacement vector. And later on we will see, when we solve the problem of electromagnetics for time varying fields, essentially we try to establish relationship between the electric and magnetic fields rather than displacement vector and the magnetic flux density. So, that time this form in the homogeneous medium, this form will be more useful. Now, the same Gauss law, now if you apply to the magnetic field and the magnetic charges. So, if we say that the net magnetic flux coming out of a closed surface is equal to the net magnetic charge or magnetic poles enclosed by the surface, that will be the Gauss law for the magnetic fields. However, we know there are no isolated magnetic poles, the magnetic poles are always found in pairs. That means, no matter what volume I take, I will always have equal number of north and south poles. So, in a closed surface, the net magnetic charges will always be 0. So, if I apply the Gauss law for the magnetic charges or magnetic poles, then there is no net charge enclosed by any closed surface. So, this quantity will be always equal to 0. So, I can make a statement of the Gauss law for the magnetic field or the magnetic flux density, and that is the net flux coming out of a closed surface is always equal to 0, because there are no net charges enclosed by the surface, the net charge is always 0. So, I can write down the Gauss law for the magnetic field, and that is the net flux coming out of the closed surface is identically 0. Again, if I apply divergence theorem to this, I will get del dot B dV, that is equal to 0. And again, if it has to be true for any arbitrary volume, then we get del dot B is equal to 0. So, the Gauss law, when is applied to the electric charges, we get del dot D equal to rho, whereas if you apply that to the magnetic charges, we get del dot B, that is identically equal to 0, because there are no free magnetic monopoles possible in practice. The next laws which we have, which relate now the electric and magnetic fields, are what are called the Amperes Law and the Faraday's Law of electromagnetic induction. The Amperes Law is what is also called the Amperes circuit law, which states that the magnetomotive force around a closed loop is equal to the total current enclosed by that loop. So, the third law which we have is called the Amperes Law or Amperes circuit law. Which says that if we have a loop and let us say you have some current which is flowing in this current, this current is going to produce the magnetic fields. If I calculate the total magnetomotive force around this loop, which is the line integral of the magnetic field around this path, then that line integral is equal to the total current enclosed by this loop. That is the Amperes circuit law. So, if I say that the element on this is given by some dl around this path and I have some magnetic field in this region which is H, let us say some magnetic field is H. The magnetomotive force is equal to the line integral of this over this closed path H dot dl is over the length here. So, this is a over this contour C. So, this is the contour C. This quantity is equal to the total current enclosed by this loop. So, if this current let us say is I, this quantity is equal to I. However, if I take a loop of any arbitrary size, it is possible that the current may not be uniform inside this loop, it might be varying from location to location. What is required is the total current. However, if the current is varying, we can write this current in the form of the current density integrated over the area of cross section. So, if I know the conduction current density inside this loop, let us say this is J, and if I find out what is the net current which is coming out of that, which is nothing but J integrated over this area, that gives me the total current I. So, I can write this also as the integral over this area, over this area A. So, this is J dot dA. So, J dot dA gives me the current flowing through a small area here which is dA. This is the direction for the area N, that is the direction for the J. So, J dot dA gives me the current flowing perpendicular to that area at this location. If I add up all those currents, that will give me the total current enclosed by this loop. So, from the Amperes circuit law, the total magnetomotive force is equal to the total current enclosed by the loop, which is nothing but the integral of the conduction current density over the area of that loop. This is the integral form of the Amperes circuit law. As we did in the previous case, we can again apply the integral theorems and can convert this relation in the differential form. So, we can convert this line integral or the contour integral into the surface integral, and that we can do by applying the Stokes theorem. So, if we apply Stokes theorem, the H dot dl, that is equal to double integral del cross H dot dA over this area A. This is by the Stokes theorem, that is equal to the total current enclosed, which is integral J dot dA. So, this quantity is equal to double integral A J dot dA. Again we can bring this term on this side. So, this thing can be written as double integral A del cross H minus J dot dA, that is equal to 0. Since this relation should be valid for any arbitrary area, this quantity should be identically 0. So, this gives essentially del cross H, that is equal to J. So, the Amperes law in the integral form is this, whereas the same law by applying the Stokes theorem we get in differential form, and that is that. So, essentially the curl of H is equal to the total or the conduction current density at that location. So, again as we saw in the previous case, this is applicable over a finite area, whereas this relationship is a point relationship. So, if we go to a particular point and if you know the magnetic field at that location, the curl of that magnetic field gives me the conduction current density at that location. Lastly, we go to the fourth law, which relates the electric and magnetic fields, and that is the Faraday's law of electromagnetic induction. So, we have Faraday's law of electromagnetic induction. The Faraday law of electromagnetic induction states that the total EMF around a closed loop is equal to rate of change of magnetic flux enclosed by that loop, and the direction of this EMF is such that the magnetic field produced by this current because of the EMF opposes the original magnetic field. So, if I have, let us say, a loop like that, and let us say we have some magnetic flux density which is given by B, we can find the total flux by integrating this magnetic flux density over this area. The rate of change of this flux density is equal to the total EMF produced around this loop. So, if I have the electric field in this region which is given as E, and if we have an element here which is dl, the E dot dl is the EMF produced in this small segment. Because of this EMF, the current will flow into this, and the current will flow in such a way that the magnetic field produced by this current will oppose this magnetic field. So, mathematically, if we write the EMF produced because of this electric field is line integral over this contour C, this contour is C, E dot dl, that is equal to minus d by dt of the total flux. Let us say that quantity is phi. So, phi is total flux enclosed by the loop. So, if I know the total flux enclosed by this loop, I take its time derivative. The negative sign essentially is to account for the fact that the EMF produced is such that the magnetic field produced by that current because of that EMF will oppose the original magnetic field. So, this negative sign is more like a resistance produced to the original magnetic field, and its role is very important. That suppose the negative sign was not there, what that means is the magnetic fields will produce the EMF, which will produce a current, which will produce the magnetic field, which will add up with the original magnetic field. So, the magnetic field will increase. If the magnetic field increases, the EMF will increase. So, essentially there is no stabilizing element here, the thing will go indefinitely growing. So, essentially this negative sign stabilizes. What that means is whenever the magnetic field try to induce the EMF in the loop and the current flows, the magnetic field produced by that current try to oppose this. So, this phenomena cannot go on increasing indefinitely. So, this magnetic field produced by the current produced by the EMF essentially try to provide a resistance to the original magnetic field. That is what essentially this negative sign represents. Now, since the total magnetic flux enclosed by this loop can be found out by integrating the magnetic flux density over this area, I can write this as minus d by dt of the total flux, and which you can find out by integrating this. So, it is integral over this area B dot dA. So, if I say here incremental area is dA, then B dot dA gives me the flux perpendicular to this. I integrate over the total area, that gives me the total flux. So, the Faraday's law of electromagnetic induction in the integral form now is written as integral C E dot dl, that is equal to minus d by dt of B dot dA. Now, this is the general relationship, that is we have a rate of change of the total flux enclosed by this loop. Now, the flux enclosed by the loop might change as a function of time in two ways. One way is that the magnetic flux density changes as a function of time. So, B is a function of time, loop is fixed, it does not change, and as a result, since the B is changing as a function of time, the flux enclosed by this loop changes as a function of time. So, I have a rate of change of the total flux enclosed. Other possibility is the B remains same, but the area of the loop changes as a function of time, and because of that the flux enclosed by this loop changes as a function of time, and again I have the EMF produced. Or I can have a combination of both, that the magnetic flux density might change as a function of time, at the same time the loop size also might change as a function of time. So, if we keep the magnetic flux density constant B constant and vary the area, we get change in the EMF. That is what is called a generator action. That is what we do in generator. The magnetic flux density is constant, and by rotating the loop in that magnetic field, essentially the projected area of the loop changes, and because of that we get induce the EMF. When the loop area remains constant and the magnetic flux density changes, that is what is called a transformer action. That is what happens in transformer. You have coils, the size of the coils is not varying as a function of time, but the magnetic field which is induced in those cores, that is varying as a function of time, and because of that we have the induced EMF. In our further analysis, we are interested in the time varying fields, that means time varying magnetic fields, time varying electric fields. So, we assume here that the space is not changing, that means the size of the loop is not changing, the magnetic flux density is changing, and as a result we say that the area of the loop is not a function of time. So, having said that we are interested in the time varying fields and not the time varying space, we essentially can bring out this derivative inside this, because now the area is no more a function of time. So, I can write down in this case, this is minus integral dB by dt dot dA. Once we do this, then as we did in the previous case, again I can apply the Stokes theorem, convert this integral into the surface integral. So, if I apply the Stokes theorem, then I get double integral del cross E dot dA, that is over area A, that is equal to minus dB by dt dot dA. Again, as we did earlier, we bring this term on this side, and for any arbitrary area A, this is del cross E plus dB by dt dot dA, that is equal to 0. And since again this relation should be valid for any arbitrary area, this integrand should be identically 0. So, from here we get del cross E, that is equal to minus dB by dt. So, the integral form of the Faraday's law of electromagnetic induction is this, whereas the differential form of the Faraday's law of electromagnetic induction is this. And again, as we said, this is the point relationship. So, if I know now the electric field at a particular location, then the curl of that electric field gives me the rate of change of the magnetic flux density at that location. Again, if we consider a medium which is not varying as a function of time, that means the medium properties which are captured by the permeability of the medium is not a function of time, I can write for B as mu into H, and if mu is not varying as a function of time, I can write here del cross H, that is equal to minus d by dt of mu into H, which is minus mu dH by dt. So, for a non time varying medium, I have the curl of electric field that is equal to minus mu times the rate of change of the magnetic field strength at that location. So, essentially what we saw that if we get these 4 basic physical laws, the Gauss law applied to the electrical charges, the Gauss law applied to the magnetic charges, the Amperes circuit law and the Faraday's law of electromagnetic induction, and write these 4 laws in the mathematical form using the vector algebra and the theorems which we have discussed, these 4 laws can be written in the integral form, but by applying these integral theorems, the same laws can be written in the differential form. Next time when we meet, we will see the inconsistency in some of these laws, which essentially was rectified by Maxwell. So, after rectification of the discrepancy between these laws, we get finally the set of equations which govern the relation between the electric and magnetic fields, and that will be the Maxwell's equations.